So given these two charges, Q1 and Q2, that are a distance d apart, separated by a straight line between those 2 points, at what point along that line is A, the electric field 0, and B, the electric potential 0? So for part A, because the inverse square nature of the electric field, any location where the field is 0 must be closer to the weaker charge, Q2. Also, in between the two charges, the fields due to the two charges are parallel to each other, both going to be to the left, and cannot cancel. Thus, the only places where the field can be 0 are closer to the weaker charge, but not between them. So here, we're going to have the electric field for part A, E equal to the constant K times charge 2 divided by x2, the distance from the point to the charge, minus K Q1, so the larger charge, divided by the distance separating the two charges, plus x squared. I'm sorry, this isn't x2 here. This is x squared, right? Because it goes as the inverse square law. It's not a subscript. That's supposed to be squared. Okay? And then we want to know where this is equal to 0. So we got to set this equal to 0. So therefore, and we're only caring here about the magnitude of the charges, Q2 magnitude times d plus x squared is equal to the magnitude of Q1 charge times x squared. Okay, now solving this equation for x, because that's the point we want to find, we find that this is equal to the square root of the magnitude of Q1. The magnitude here is important, obviously, because if we have a negative charge, then the square root of a negative value is going to give us an imaginary number, and we don't want that. We don't want to deal with that. Divided by the square root of the magnitude of Q1 minus the square root of the magnitude of Q2. And then this is all multiplied by D. Okay? Well, plugging in the values we were given for this, we find that this comes out to equal 17.4 centimeters. And that's going to be left of Q2. So we can write left and box that in as our solution for A. Okay, now we're going to do something similar, except this time we're going to find it where the potential is equal to 0. So let's start a new page, and this is part B. Sorry about that. There we go. Okay. Well, the potential due to the positive charge is going to be positive everywhere, and the potential due to the negative charge is going to be negative everywhere, right? So since the negative charge is smaller in magnitude than the positive charge, any point where the potential is 0 must be closer to the negative charge. Does that make sense? So consider locations between the charges. Consider the location between the charges. We're going to call it x1, and to the left of the negative charge, x2. And I'm just going to draw a little diagram so you can see what I'm saying here. So we're going to say that here is Q1, and then they're separated by a distance d. And here is Q2. Okay. So then the values that I was just talking about, the values, actually here, I have Q1 and Q2 backwards here. Wasn't matter too much, but this is how I had done it. So let's keep it consistent. Okay. So the value x1 here is to the right of q2, and to the left of q2 is going to be the value x2. So to this point here, we're going to call this x1. And then to here, we're going to call this x2. Okay. So then the potential at location 1 here that we're going to calculate, we'll call this V1, is going to be equal to the constant K times Q1 divided by, and potential goes as inversely proportional to distance. So this is going to be D minus X1 for Q1, right? Plus K times Q2 divided by the distance x1. And then we want to know where this is equal to 0. Okay, so solving for x1, of course, the k's are going to cancel. We find that x1 is equal to q2 times the distance d divided by q2 minus q1. Plugging those values into this expression, we find that this is equal to 1.1 centimeters. And we can box that in as our first solution, where it's 0. Then for V2, we're going to do the same thing except for location 2. So this is going to be K Q2 divided by the distance plus x2 this time, right? Since it's to the left, minus a negative is a plus is plus. So this is going to be K times Q2. Oh, there's a typo here. This is Q1, right? Because we're considering the first value, distance from Q1. And then for Q2, it's going to be divided by just x2. Okay, so now solving this equation for x2, we find that this is equal to minus q2, times d divided by q1 minus q2. So plugging those values into this expression, we find that this is equal to 8.1 centimeters, of course, to the left of q2. We'll box that in as our solution to the second part of that question.